class. I don't know if anybody could name this molecule. It's not a learning objective in this class to be able to name that, but it's a very common precursor to materials that all of you have come into contact with at some point. A few years ago, there was a train accident in Ohio, and a train car carrying a bunch of this chemical tipped over, started on fire, and burned, releasing all of this and its some combustion products into the atmosphere. This is not methane. This is vinyl chloride, which is the precursor to polyvinyl chloride, which you guys all know as PVC. Anytime that you've come in contact with PVC piping, you've been dealing with polyvinyl chloride, which is the polymerized, many units bonded together version of vinyl chloride. And when this burns, it actually produces hydrochloric acid. So you are getting not just toxins from combustion, but hydrochloric acid in the rain that fell after it. Based on this Lewis dot structure, raise of hands, how many pi bonds in vinyl chloride? Ashley? There are not 5 pi bonds. You said what? Just one. Good. So in all of the positions where you see bonding, those are all sigma bonds, except if there's multiple bonds there. And there's only one region where we see multiple bonds. One of those bonds is a sigma head-on overlap of orbitals, and one of those bonds is a pi side-on overlap of p orbitals. And this was one thing I didn't get to clarify yesterday, but those sp hybridized atoms, they can make 2 pi bonds because they have 2 p orbitals that haven't been changed. They're still normal p orbitals that can do side-on overlap. Whereas sp2 atoms can only make 1 pi bond. And how many pi bonds can sp3 atoms make? 0. Until you start looking at things like sulfur, phosphorus, and those larger atoms that can expand their octet, because those can become sp3 hybridized and make pi bonds. They do some really funky stuff. 9 times out of 10, though, you can follow this trail with molecules, and you can figure out, based on the hybridization, how many pi bonds it can make, and often work backwards. So there's 1 pi bond in vinyl chloride. How many sigma bonds? That one's 5. There's 5 different bonding regions. 1, 2, 3, 4, 5. All of them have 1 sigma bond. There are 6 total bonds in vinyl chloride. And I forgot to show this the other day as well. This is in your textbook. This is a nucleus here, and it's actually showing hybridized orbitals in yellow. And you'll see that one of the hybridized orbitals comes to overlap with an s orbital, that's a sigma bond. A hybridized orbital head-on overlap with an s orbital, sigma bond. And then here, a head-on overlap of 2 hybridized orbitals, a sigma bond. And this is the side-to-side overlap of the p orbitals. You'll notice in this picture, though, that they don't actually overlap. This is what they look like when they overlap. It's like they get ballooned out and they stretch. Down here, what you're seeing is the head-to-head overlap of a sigma bond, and then a p orbital that is going in and out of the plane of the board, overlapping with another p orbital, side to side. You'll see that you've got red to red, blue behind the red to blue, and then you've got another p orbital that's sticking straight up and down, red to red, blue to blue, and again, when you balloon those out, this looks a little bit funkier, right? Like, can you easily tell which red lobe belongs with Which blue lobe? No, not at this juncture. But you get familiar with this shape, this ballooned out p orbital, and that's what a pi bond looks like. Remember that electrons look like this shape. This is where the electrons are. So when those orbitals overlap, when they get stretched out, now the electrons are just in a larger region. They're spread out further. Does anybody remember the name of the theory that this is all based on? It's not Lewis structure theory, and it's not Vesper theory, but bonding here is predicted by valence theory. There is another bonding theory. It's called molecular orbital theory, otherwise MO theory. And this will not be on your unit test, and it will not be on your midterm. So I'm not going to spend a lot of time on it. However, it is on your real chem assignments, and that sucks. So I want to give you some background because I think it's actually pretty easy to justify. Valence bond theory says two atoms overlap their orbitals, and now the electron can exist in both orbitals at the same time. MO theory says orbitals from two different atoms combine in the same way that we saw hybridized orbitals are just the combination of different orbitals. They combine to be no longer atomic orbitals, but two or more atomic orbitals combine to become a molecular orbital, an orbital where the electrons are spread out across the molecule. In fact, that's what this kind of looks like. This is a molecular orbital because you can see it spread out across more than one nuclei, whereas this and this are atomic orbitals. And we get these diagrams. We say that we take two atomic orbitals and we set them in these two lanes. And we can say something easy like an s orbital. If those two s orbitals are in phase, meaning their mathematical equations have the same sign, then they have this constructive interference, and they actually stabilize better. And if they're out of phase, meaning one is plus and one is minus, they destructively interfere, they destabilize their energy. And we call this no longer an s orbital, but we call it a sigma orbital because it represents a sigma bond that has been created. It's no longer an s orbital, it's a sigma orbital. And specifically, we call it a bonding orbital. When electrons exist there, they create a bond. But at this destabilized energy, where the orbitals actually cancel each other out, we get what looks like two different lobes. This is called sigma star, and it's considered an anti-bonding orbital. That is to say, if I take electrons from something else and I can occupy that orbital, I can break the bond that exists between the two atoms, and I can send them on their merry way. So I want to take a look at the real chem assignment with you guys. Cole, do you remember, was it in the module or the unit checkpoint only?
No, it was in the module that confused me. There was that one draft, and then it also asked a ton of weird questions.
Also in the unit checkpoint. All right, so let's see what they give us in here. Here's an energy diagram. This is simply saying why atoms bond together. Their electrons get lower in energy. And we're looking at different bond lengths, different energies associated, not MO. Here, valence bond theory, we're just looking at the head-on overlap of different orbitals. This is valence theory. This is just deciding, based on the Lewis structure, what the hybridization must be. This is similar to things that we've done. More valence bond theory, just deciding the types of bonds that are there. And then we've got question 6, the molecular orbital diagram for Li2. It wants you to draw it and then consider this. This is the molecular orbital diagram for Li2. It's also the molecular orbital diagram for H2. The only electrons that they will overlap are in their s orbitals. So we say that the sigma 1s is actually 2 electrons, and the sigma 1s star is 2 electrons. That is to say that lithium's core electrons in the 1s shell, they fill both the sigma and the sigma star. Then we get sigma 2s, and this is what has 2 electrons in it, versus sigma 2s star. This is in the valence shell. This doesn't have any electrons in it, and this is what would allow lithium to bond to itself. When we say that a sigma orbital is filled and a sigma star is also filled, that cancels any bonding order. They have 0 bonding order. But if sigma is filled, sigma star is unfilled, that gives us a bonding order of 1. Oh, what a terrible, terrible thing. You know what? Here's a modification. I will go through these 2 checkpoints. Maybe not in advance of the midterm, but maybe next week I'll be able to do this. I will go through these and adjust your grade so that you don't get penalized for not submitting MO theory questions. How does that sound? That sounds better than asking you to just try and figure this out, because there's a lot going on in here. And none of it is useless. This is all very useful information. But when it gets to this magnetic stuff, this is just too far. It's talking about whether we have unpaired electrons or not, and we don't have unpaired electrons. This is another MO theory diagram. And it's showing you what I've got there, except with s and with p orbitals. There's some really cool stuff. Like, for instance, you could all sketch oxygen at this point. You could draw the molecular, the Lewis dot structure for oxygen, and you would think that oxygen has a sigma and a pi bond, and 2 lone pairs on each oxygen. But oxygen actually looks like this, where the pi bonding is completely filled and the pi star is half filled, which means that it cancels out one of its own pi bonds. It's Lewis structures are like explaining molecules to kindergartners. They get the idea across, but it's shortcutting a lot of the actual mechanics of the molecule. MO diagram looks at what the molecule actually does. But again, it's not on your unit test, it's not on your midterm, so it's not something we're covering. For that reason, if you see MO diagram questions, molecular orbital theory questions, you can skip them on both the Module 11 checkpoint and the Unit 4 checkpoint. Does that sound good? If you're confused about it, just let me know. If you've already submitted it, or if you want to do them, maybe I'll give you some extra points for doing them. Deal? Okay. What do you guys think about bonding? It's pretty, isn't it? That's electrons, give or take. All right. Any other questions on this old material before we move ahead? Great. We're doing Unit 5 today, which is 2 modules, Module 12 and Module 13. Luckily, these are all pretty much conversions, math calculations. You all brought your calculators today that you'll be bringing with you to the midterm next week. The midterm is on Canvas, just like the unit test. All multiple choice, just like the unit test.
We get like a formula sheet, right?
You will be given a formula sheet on the midterm.
So, like we don't need to bring one.
You do not have to bring it.
Okay.
And here's what it looks like, in case you forgot, so that you don't have to guess what's on it. It's the midterm equations sheet. I didn't name that, by the way. That's how it's named, possibly useful equations. These are the equations that you're given. You'll actually notice that some of the equations we're going into today are on here. But there is something that's not on here that I wanted to show you. By the way, if you're grabbing a sheet, grab two. Don't grab one. These packets are two. If you do not have two sheets, come back up and grab the other one. There are two different roadmaps on them. They're similar, but different. Sorry about that, guys. Maybe we can just make I should have printed them into two different piles. If you need to grab one, leave the other in a different pile. All right, we're starting on this front page that says one-step calculations, one-step conversions at the top. Here is a conversion roadmap that your textbook gives you. Mine is laid out similar, but with a little bit more information. You'll notice here that it says mass of a substance, grams, moles of a substance, mole, moles of an element, moles, grams of an element, grams. They're being specific about what is being converted. A substance, like water, an element, like the hydrogen in water. You can convert between the amount of moles of each of them. The roadmap that I've given you is a lot more generic. It says moles of A, moles of B. It doesn't matter what A is, it doesn't matter what B is, but this is your conversion. And then I'm actually a little bit more specific. So I don't just say molar mass, but I tell you that to convert between the mass of A and the moles of A, you need the molar mass of A. If A is water that you're considering, you need the molar mass of water. If A is hydrogen that you're considering, you need just the molar mass of hydrogen. I also have this split into a different direction where the number of moles can be converted into particles as well using Avogadro's number. And then in the middle, what I introduce here is a mole to mole ratio or a mole ratio. Mole ratios are the number of moles of A over the number of moles of B, but we can write ratios any way we'd like to, which means that we can flip this ratio upside down whenever we need to. These two moles have to be related somehow. So let's talk about, I do water too much. Let's do something else that's a little bit, it's still common, but I talk about it a little bit less. This is ammonia, NH3. Can you give me the mole ratio for the moles of NH3 to the moles of nitrogen? Can you also give me the mole ratio for the moles of NH3 to the moles of H? Let me walk through the first one with you. When I have 1 mole of ammonia, it is a random number, but it's convenient because it just sets it to 1. When I have my compound ammonia, how many nitrogen atoms are present? 1, which means the ratio of ammonia to nitrogen is 1 to 1. So we can set these ratios however we want to. There's only one true ratio, but we can set it to be as easy as possible. When looking at the mole ratio between ammonia and hydrogen, every time I have 1 mole of ammonia, how many moles of hydrogen do I have? 3. If I have 3 dozen sandwiches, how many pieces of bread do I have? 3 dozen? No, because a sandwich, unless it's open-faced, a sandwich has 2 pieces of bread. So 3 dozen sandwiches with 2 pieces of bread each, 6 dozen pieces of bread. That's the mole-to-mole conversion. When I have 1 of this substance, how many of the things it contains do I have? Notice how the subscript for hydrogen became the coefficient down below. This is probably the most challenging part for you. But I want to remind us about molar mass as well. I don't think that I really got to introduce molar mass when we did this back in Unit 2. Molar mass is the sum of the atomic masses in grams to give you 1 mole. And I do want to point out again, despite mole only being 4 letters long, it's often abbreviated to 3 letters, MOL. On your periodic table, the masses that are reported have what unit? Anybody need one? You'll need this for calculating molar mass today. AMU, atomic mass units. The mass that's reported on here is per atom. This is no longer per atom. This is per 600 billion million molecules. 600 billion million atoms, roughly. So when you take the mass on here reported in AMU and you multiply it by Avogadro's number, that mass becomes a mass in grams, only if you have 1 mole of a substance. So the nice thing about molar mass, it's also a ratio. You get 2 units. And this bottom number with moles is always 1. It's always 1. You never have to guess here what number goes with moles. Here we had to kind of guess. We said, well, let's say I have 1 mole of ammonia, then I have 1 mole of N. If I have 1 mole of ammonia, then I have 3 moles of H. This is never a guess. Always 1. I guess the last number that you need in order to do any of these calculations is Avogadro's number. And this is not a number you have to worry about. Sorry, let me repeat that. It is a number you have to worry about because it's not on here. Avogadro's number, 6.022 times 10 to the 23rd. It's also technically a ratio, but one of the units is a bit vague. This is per 1 mole of things. And so the unit that goes with the big number could be ions, atoms, molecules, cars, galaxies, whatever you want it to be. So we can just say things, and you can substitute that. All right, a word of advice in doing calculations. Some people will tell you that if you want to convert between mass and moles, you should multiply by the molar mass or divide by the molar mass, depending on which way you go. Personally, that never works for me. I cannot get it in my head to say, going in this direction, I divide by molar mass, and going in this direction, I multiply by molar mass. It just doesn't make sense. What makes more sense to me is to set up these conversions. If I have 5 moles, now I know where to place moles. I'm going to put moles on the bottom, and I'm going to put grams on the top. So in this way, I'm multiplying by the molar mass. If I'm going in the opposite direction, and let's say I have 40 grams, then I know that I need to put grams on the bottom, and moles will go on top. And in this way, I'm dividing by the molar mass. That's the way that makes the most sense to me. I'm not going to encourage you to do it this way inherently. So if you want to figure out from moles to grams, multiply, from grams to moles, divide, that's great. But this is a little roadmap that you can write down on your cheat sheet, bring with you into the exam, and it can help you figure out when you're going to need what conversions. All right. Here's the deal. I've split this up into 1-step conversions, 2-step conversions, and 3-step conversions. That means 1 step, you're just moving along one of these arrows. 2 steps, you have to move across 2 of those arrows. And in the 3-step conversion, you're moving across 3 of those arrows. That's to kind of give you this perspective that there are different numbers of conversions you can have to do. Do you want to go through one of the conversions together and then have some time to finish the rest of them on your own? All right. Let's do step number 1. We want to find the mass in grams of 0.10 moles of copper sulfate. You can start anywhere you'd like to with conversions, but I like to start with what I know. And in this problem, what I know is that I have 0.1 moles of copper sulfate. I'm also going to encourage you in your conversions to be as explicit with units as possible. Don't just put moles of copper sulfate. I don't want to know moles anymore, I want to know grams. So if I'm looking at my roadmap, let's say that I know moles of A, which way am I trying to go on my roadmap? Am I trying to go to the right to moles of B, down to the left to grams of A, or up to the left to particles of A? Which way am I going? I'm at moles of A. That's the information I have. Which direction am I headed? Up to the left, I want particles of A. Down to the left, I want grams of A. So that means I need to know what other conversion factor. I need to know the molar mass. And that's actually going to become obvious when I put moles of copper sulfate on bottom and grams of copper sulfate on top. Whoa, whoa, whoa. How did I know to put moles on the bottom and grams on the top? I want them to cancel. I need moles to cancel. I really don't care where grams goes. That's not true. I do care that grams ends up on top. But grams will end up on top when I get moles to cancel. All right, now we do a calculator exercise. Grab your periodic table and your calculator and add up the mass of copper sulfate. Copper in the transition metals, element 29, has a mass of 63.546. Plus, I've got 1 sulfur, element 16, mass of 32.065. Plus Here I'm going to use parentheses on my calculator because I've got 4 oxygens. So I want to add the mass of those 4 oxygens, but I want to multiply. Plus, parentheses, 4 times 16. And I get a mass here. Molar mass equals 159.52 grams per mole. Anybody get something different within rounding? That's within rounding. Yep, 0.61. That's okay. That means that you might have actually put 15.9, or you might have rounded a little bit differently. That I wouldn't be worried about. Anybody else? Different number? All right. We've calculated the molar mass. Where does that number go, 159? Does that go on top with grams or on bottom with moles? On top with grams. Because it's literally saying 159.52 grams. Per how many moles? Per 0.1? No, if you added it up from the periodic table, then you are assuming 1 mole. Okay, do I have 1 mole? No, this is the conversion. If I had 1 mole, this is how much it would weigh. But I don't have 1 mole, I have 0.1 moles. Should my final number be larger than 159, equal to 159, or smaller than 159? Smaller. I have less than 1 mole. My mass should weigh less than 1 mole does. Not hard math to do here. 15.952 grams. Oh, with 0.1? You're right. On the document, I think I put 0.10. So this would have been 0.10. Lizzie, where do I round then? What should my final answer be? Yeah. This is my second significant figure, so the 9 rounds my second sig fig. 16 grams of copper sulfate. All right? Now I want you guys to do the next 2 conversions. Or do you want it? Should we go through a 2-step conversion while we're at it? Yeah? So there's only one 3-step conversion, so I'm going to make you guys do that alone. Do you want to do number 4 or number 5? 5. Very quick answer. All right, so problem number 5 says, I want to find the moles of sodium carbonate. I did this intentionally to you guys. I didn't always put chemical formulas because something we learned in Unit 2 were names. That's coming back. You still need to know those names. You still have to figure out how nomenclature informs chemical formula. Who has the chemical formula of sodium carbonate? Give me one part of it if you don't know all of it. Na is in there. I know that this is going to have Na. Anybody know the chemical formula of carbonate? CO3, 2 minus. That makes this an ionic compound. So how many sodiums to balance a carbonate? 2 Na plus to balance 1 Na minus, CO3, 2 minus. Na2, CO3. So how many moles of sodium carbonate can be made with 1.204 times 10 to the 24 ions of sodium? I'm just going to write that as Na plus. Can you tell me where I am on my roadmap conversion? It doesn't matter if you choose A or B, that doesn't matter. But am I at particles, grams, or moles? What information do I have? Particles. The only place I can go from particles is to moles. and that stays within the same substance. So I'm going to go from particles of sodium ion to moles of sodium ion, and from particles of sodium, or excuse me, from moles of sodium ions, where do I want to go from there? I want to go to moles of sodium carbonate. In order to go from moles of sodium to moles of sodium carbonate, what do I need? I need a mole ratio. So I need to know how many moles of sodium ions are in 1 mole of sodium carbonate. Subscript 2 with sodium, just like subscript 3 with hydrogen. That's my mole ratio, 1 to 2. All right, so let me set this up. 2 conversions, so I'm going to have a little bit of a bigger box. True or false, you have to do all the conversions at once. False. You can absolutely do one calculation, get a new unit, set up a new calculation, get a new unit. It just takes a little bit more time. So I know that I have 1.204 times 10 to the 24 ions of sodium plus. And I want to go from ions of sodium plus into moles of sodium plus. Correct? That's what my roadmap says. Particles to moles.
How did you only write the sodium plus? Why didn't you add the carbonate atom to the end of that?
Because I don't have that. It says that I have this many particles of sodium ions.
Oh, okay,
I want to know how many moles of sodium carbonate I can make, but I don't know how many moles of sodium carbonate I can make.
never mind.
All I have information about is sodium ion. What numbers should I fill in there? Avogadro's number, correct? Well, where should I fill it in, Ryan? Avogadro's goes in the bottom. Avogadro's goes on the top. Which unit will Avogadro's number follow? Things, yep. And what number will always go with moles? 1. It will always be 1. 1 mole is 6.022 times 10 to the 23rd ions. Let's do the next calculation, the next units, rather. Notice how number of ions cancels. I need to get moles of sodium ions to cancel as well. So I'm going to put moles of sodium ions on the bottom. And what should I put on the top? My what? No, what unit should I put on the top? I think somebody said it. Moles of sodium carbonate. Because that's what I'm trying to get information about. I'm trying to find out information about sodium carbonate, given information just about sodium. All right, now I need my mole ratio. What number should I put on top? What number should I put on bottom? What number should I put on top? 1. And what number can I put on bottom then? 2. This is not the only accurate ratio, by the way. You could have also put 0.5 and 1. If I have 1 sodium ion, then I have half a sodium carbonate. That just feels weird. So it's nicer to put 1 and 2. Notice how moles of sodium ion cancels. The only unit I'm left with is moles of sodium carbonate. All right. We plug this into our calculators. I just met with a student yesterday about calculators giving them some issues, and it had to do with these big numbers. When they plugged in something like 1.204 times 10 to the 24th divided by 6.022 times 10 to the 23rd, here's what their calculator did. It took this big number and then divided it by 6.022, gave the answer for that, and then multiplied it by 10 to the 23rd. So they were getting times 10 to the 46 as their final answer. Not helpful, right? The calculator was forgetting that they wanted this number to be just one thing. It was screwing up the order of operations. So how do I recommend getting around that? Put parentheses. So parentheses, 1.204 times 10 to the 24th, end parentheses, divided by parentheses, 6.022 times 10 to the 23rd, end parentheses. What number do you guys get? Did I hear 1? 1.9996? 0.999. Oh, as your final answer. You're doing the final answer. Sorry. I was just doing this. You get something like about 2, and then divide that number by 2. I'm not getting 0.999, but how many sig figs can we round to here? 4? Well, I've got 4 sig figs here. 2 is a whole number. That's a counted number. So 2 is not limiting my sig figs. Is that what you were thinking? So I actually get 4 sig figs here, 4 sig figs in Avogadro's number. So I should be limited to 4 sig figs in my final answer. Here's what my calculator gave me. I got 1.026 moles of sodium carbonate. What did you guys get? 1.9? No. 0.9996. And that's with 4 sig figs? They're pretty close. I don't know where our rounding went different. But it is what it is.
How do you get this number? Because I was dividing the first number by 7 and then dividing it by 2. And
7?
no, by 7.
Oh, okay, yeah,
And then this answer divided by 2.
correct.
And I got 0.9996667.
Yeah, I don't know why you guys are getting a different number than mine. 0.9996 moles of sodium carbonate. But this is a good example. If you're on the unit test or the midterm and you plug in a calculation and you get a number like 1.026 and the only available answer is 0.9996 and that's the closest answer, you can see how those are very similar numbers, right? If we were to round this to just 2 sig figs, we would have the same number. So in that way, I think you can feel confident in saying I've done the calculation right, just not me doing the calculation right. I don't know why your numbers are different. I'm going to plug mine back in and see if I can get something else. I get the exact same number again. You guys aren't rounding anywhere, correct? You're just plugging it all straight in. You're doing 1.204 and 6.022. You're not doing 6.02? Yeah, I don't know what to tell you. That's really weird. If anybody wants to plug it in on my calculator and see if you get your number again. What questions do you have on one-step conversions versus two-step conversions? Was this too confusing for you? Break it into 2 one-step conversions. What questions do you have on the roadmap? Can you land somewhere? And then can you move all the way through to the next part? All right, spend the next 15 minutes working with pairs. Work with people around you to do these conversions. Again, if you feel confident on your math, good. Lean into helping your classmates because that's only going to help you more than just doing your own math. Help them identify their shortfalls and how to set them up better. When you explain it to somebody else, it validates it in your own mind. No answer key yet. This guy.
Oh.
Is that how you set up yours?
Yeah.
You take the time to do like these huge fractions?
Yeah, because if you multiply, you don't need parentheses. The problem with the parentheses is when you divide them.
Yeah. Interesting. So you just set it straight up into a.
Yeah, I just did like all of it.
It is still weird though that the exact same numbers in the exact same functions.
Yeah, we were having that problem earlier. It's because, yeah, when you divide, you need parentheses in like a certain place.
Yep. That's the issue that I found that I was just sharing about. Okay. That's so weird. Oh, guys, it'd be 9997.
Yeah, 997. I was gonna say something, but
That 66 gets rounded to 7. He made it work on my calculator. Are you guys setting it up as like multiply by a 1 over and then multiply by 1 over? Or are you setting it up as parentheses divided by parentheses? And you still got 0.9997.
I just do it, so instead of having them put the word in the parentheses, you do the one small section and you get an answer, and then the calculator just saves the answer, so then you can do
And I did that too the first time. I got my number twice. Very weird. I want you guys to see how much of that front page you can finish in these 15 minutes. One thing that I want to talk about with these problems, the wording is very confusing. So what I want you to do when you're reading it is highlight or things that are important. So like moles. Okay, this is important. I know that my answer is moles. And then we've got this. This molecule. That's my ratio. So this is a one-step conversion. Where am I starting? Do I start at particles, mass, or moles?
that's actually confusing when I was doing it.
Mm-hmm. Let that be like,
How many
right.
hydrogen atoms?
And that means that I'm converting where? Just to moles.
No, but in this
That is
you
your
multiply
source.
2 over 1. So yeah, times 1 over 2. So you just flip that ratio.
That's right. Good. You want to set it up?
So yeah, why would you flip it?
So it's gonna be.
You'll touch it.
Well, this is for hydrogen.
Yeah.
Good. Okay. Yes. You got it.
Where are you?
You know, I'm not holding it up.
So either way, it doesn't matter.
Right.
It feels pretty good.
Oh. Here, you know. All right.
How do you know which ratio you want? It would have to be like, it'd be like what you're looking for.
Yeah.
So like, in this case, it'd be oxygen.
Good. I'm just trying to figure out. I tried to set this one up first before I started working on this one. I was working through these last night on okay? And the way that I was setting up these set problems was different than how you So I was just checking to see if I still got the right answer, but I got a few
Yeah.
decimals off, or a few.
Well, that's because you ended up multiplying by 2 on top, and we knew that we needed to divide by 2. In fact, here's an issue with this setup. Molecules doesn't cancel with moles.
Oh yes, I'm so sorry. I'm gonna switch it.
That's what,
So this
yeah,
is what's
when you switch that.
So divide by.
That's right. And the units actually tell you that. The numbers are less relevant. The units are most relevant.
Okay.
Right? And now when molecules cancel, you're left with unit moles.
Iron peroxide is.
Here's an issue. So you started, you didn't say it was sodium ions. You said it was ions of sodium carbonate. The question tells us that we have this many ions of sodium, but in your unit you said ions sodium carbonate.
Yeah.
That's not what it says.
Yeah, I was confused. Like, I asked you that, and then you said, and it made sense. You said that, like, the second part of the question, which I just, like, skimmed through, like, that's why we only included sodium.
Yep, yep.
But then
Oh,
I
and
was
it's
like,
not
wait.
Na2 either. Sodium ion is Na plus. Sodium carbonate does have 2 ions of sodium, but sodium is not Na2. Like here, you're saying ions of Na2. You're extracting that out of sodium carbonate, but that's not what it is.
We're just being asked for
Sodium
sodium.
ion. And I think this is maybe another place where maybe your units got thrown off. So here, yep, up here. Good.
But the
And
final
then,
answer was not right.
well, actually up here, when you said 2 moles of sodium to 1 mole of sodium carbonate, Na2CO3. Or in other words, this is A, this is B. They're different chemicals. Sodium ion, sodium carbonate.
Yeah, we can try
Okay.
more.
Here, when you were trying to, this was when you tried to set up first. So you actually tried converting from ions into moles, but you used the molar mass. We should use ions to moles. We need Avogadro's number. It's only from mass to moles that we need molar mass.
That
Here's
makes
a
more
way
sense.
that
I'm
we
gonna be
can.
honest, I didn't really understand this math, but
That's okay. I know
that makes more sense. So I'm going this direction.
That's right. That's right.
Okay.
And then think about the units. Ions, you actually have grams here.
Yeah.
They don't cancel, right?
Yeah.
So that's probably why that number got thrown off.
Okay, thank you.
You bet. Yes. Well, first of all, you lost your unit. Mole of H2O cancels. Mole of O cancels with mole of.
No, the one over two is
Moles of O cancels with moles of. Oh, good. Moles of O, grams of. A little bit. We want molar mass of A, so that's grams per mole of O. So you put the molar mass of water. We need the molar mass of oxygen. Correct. Okay. Yep. Good. This number looks correct, but it's not what's out of grams. We want to know how many. Oh, so it's actually also. We want to know how many moles of oxide. This is particles.
Yeah.
Moles cancels, and you're left here with ions. Yeah. You did write moles, but that's actually not true. And then the other problem is, this is how many moles of iron
Yeah,
oxide we have.
well, that's the total.
I need to know, or I want to know how many moles of oxide we have. that means I'm starting here. I use free oxide. I need to convert to oxide, and then I can convert to. Oh, that's it. It's just one step. So I'm here. I want to get here.
Okay, yeah, that's what I got too. I just need to round it. Yeah.
Well, you have the, you know the chemical formula, right? So if you know the chemical formula, you can extract the mole ratio. It might help if you show your work.
What?
I know.
What?
And if you have a pencil, it makes it even easier. So let's take a look at this. We know moles of water, so that means we're starting here. I know moles of A.
Actually,
I want to know
Wait, how did you
if
select this? The third one.
water is A, oxygen.
I thought I used. It's kind of like the fifth
My
one.
first conversion is going to have
How many moles of oxide ions are in 5 grams of fire?
and then I want to know grams of oxide. So I'm going to go into moles of oxygen, grams of oxygen,
Oh, wait, no,
using the molar mass of
Yeah.
oxygen.
Do you know what the?
What you tried to set up was
Yeah, it's
moles.
Fe2O.
This is not the protein. This would be particles.
Start out with
third moles.
5 moles.
If you're doing
Yeah.
18 grams, that would be per 1 mole. But I actually don't want to go for grams of water, grams of water. That's going this way.
Okay, yeah, that makes sense. So it is kind of setting it up.
I want to do first
Okay.
conversion from moles of water to moles of oxygen. Guys, if I can give one tip in setting up conversions, it is forget about the numbers until you have set up the units correctly. Your units will guide your conversion. No numbers necessary. And some of these numbers are like ridiculously long to write out. So only fill in the numbers. Once your units cancel in a way that give you the unit that you want. I want to go through the examples together in a little bit, but take that advice and start by laying out the units that you need, and then fill in the numbers that you need. So we know how many where does that place us?
I don't think it would be.
We got mass of B. What's the only thing we know?
Wait a minute.
So then we go grams plus 1 called 1, 2. So we're actually, this is our roadmap, right? We're going to go from mass of A to moles of A, moles of B, mass of B. We're going to take this thing out.
That is the right answer. It's just like, I was trying to look up, like, how can you?
I know. It's kind of like how when you have a...
It's just talking about the oxide ions.
No, it's fine. You did it. Okay, then our- No, that's
So
correct.
this is the
Well, actually,
in grams of iodine, right?
not true. I think you could say
Well, this is
one mole of iodine. 1 mole of 3, but that would not be the protein. You have 3 moles that
It like sounds
Yeah,
wrong,
correct.
but like,
This is correct.
okay.
Moles of
For
oxygen.
iodine, it's what? For
Yeah.
iodine.
Okay.
Like I
I'm not good.
Yeah, and then there's 1 mole of O and 1 mole.
I think you're right.
And then 1 mole of O.
Yeah. I'm just taking my time with these. I try to set this up different.
You were. You got it. You got it. And here, you're almost set. You got
How
your
many
conversion.
Yeah, but
Number 3. Okay, so we know that we have 5 moles of iron trioxide. Where does that place us in our roadmap? Moles of iron.
we want to mass of iodine,
Moles,
which is
so I need mole to mole ratio. So first of all,
This is iodine.
I can start to say 5 moles
is a
You have the chemical formula? You do.
For one iodine.
Did you Google it?
Oh yes.
You worked it out?
Just be.
Great. Because that's what you're going to have to do on the unit test. Right? So we know we have 5 moles of Fe2O3.
Is it literally just the
I need to get out of moles of FeO3. I need to get into moles of O. Oxide is O2 minus.
So
You have 3 oxides.
there's
of
a
iron
certain
three.
amount in
Fe2O3. That's 3 atoms, 3 ions of O.
you don't have to do less like 5 more.
Which is.
And I thought it was 5. I was close. I think so.
Actually, oxide has what?
Yes, right.
O.
But it says,
Minus.
yeah, because there's
Probably.
O2 minus. And there are how many O2
And did you put the
minuses?
atomic mass on top? Or the
This is
Your molecular ratio is
one
not
mole?
1 mole of iron dioxide is 1 mole of O3.
I'm so confused. Okay, this one's like a
3 moles. 3 moles.
And the grams
In your
is like
chemical formula.
the molar mass.
like an atomic
What? Yeah. Yeah, these definitely do for like the questions. Like my Okay. Okay.
That means that I'm going to put
And then
5 moles of
over
O.
one mole of oxygen.
I think we would be multiplying O by 5.
The only thing I'm unsure of is
Yeah, okay. I've got a dozen feed some people. How many pieces is bread?
You have no idea what it is? Like the significant figures. I'm like, oh, for this? Yeah. Because it's just one. It's just one. So I guess it's just one significant figure.
How can I?
And then you round the point to. Oh. That's actually so. I assume that because there's like no like decimal. Yeah, it's like. Yeah, well, I run. I don't know if you remember. I grew up in how many numbers from like 5 to 15? But it figured it out because it's so I think that's what I was I think so.
Okay, oh, here you go. That's not bad.
I know. Did you get the molar mass of 27?
This is set up correctly.
306.
Moles of O.
For oxygen? No, for H2O.
So it is 16, and the conversion of it is 1 to 1.
Grams per H2O. Okay, wait. So I'm just converting. Okay. Moles of water, you have 1 mole of then you just oh, you only put the atomic mass of oxygen. You're not putting the atomic mass of hydrogen.
Question.
Yes.
Just oh, okay, yes.
On number 6, like, to get from moles of A to moles of B, you need your mole ratio. What is the ratio in this?
It's like no accents. Yeah.
You gotta know the chemical formula.
16. Around that.
What's the chemical formula?
Moles.
That's 1 to 1.
Yeah.
Well, it should just be.
All right, are you guys ready to go through some of these? Let's look at our other one-step conversions. How many moles in 1.5 times 10 to the 23rd molecules of methane? Do I need to know the chemical formula of methane? No. If I look at my conversion map, I'm starting here at particles of something, and I'm trying to get to moles of that something. What's the conversion factor that I need? Avogadro's number. So, I've got particles. I'm going to put particles on the bottom, moles on the top. Those are the units of Avogadro's number. Where does Avogadro's number go? with particles on the bottom. What number did you guys get when you plugged this? No, sorry. What number goes with moles? 1. What number did you get when you plugged this in? Good. That's 1/4 of a mole, 0.25. If the numbers came out nice, that's because I was trying. All right, another one-step conversion. Guys, I want you to recognize the one-step conversions that we did were moles to mass, particles to moles, and now number 3 is moles to moles. I just picked pieces along this roadmap to give you examples of those conversions. So I'm starting here with 5 moles of iron 3 oxide. Did you figure out the chemical formula of iron 3 oxide? What is it? Fe2O3. That's important because landing here at moles of A, moles of iron 3 oxide, I'm trying to go to moles of B, and that means I need to have a mole to mole ratio. Moles of what goes on the bottom? Yeah, moles of iron 3 oxide. Moles of what go on the top?
Oxide.
Oxide, which has chemical formula O2-. It's not surprising that some of you thought that we'd be converting to moles of O3, but there are 3 moles of oxide in 1 mole of iron 2 oxide. Notice how the subscript became the coefficient. That's really what we were looking for there. And then somebody else said, how can I possibly have 15 moles of iron oxide if I only have 5 moles of iron 2 oxide? How can I have 15 moles of this? That's the example with the sandwiches again. If I've got a dozen sandwiches, I will need more than a dozen pieces of bread because big thing has many small things in it. 2-step conversion. How many grams of oxygen in 1 mole of water? Where do I start? Where am I landing on my conversion map? I'm starting with moles of A. That's the information I know. I know how many moles of A I have. I have 1 mole of water. All right, this is a 2-step conversion. Which way am I headed? Do I want to know anything about the molecules of water or the mass of water? No, I want to get out of water and I want to get into oxygen. That means I'm going from A to B. Those are different chemicals. So I need to go from moles of H2O to moles of O. That's a mole to mole conversion. No numbers. I have another conversion I want to do because I don't want to know how many moles of oxygen are in 1 mole of water. I want to know the mass of that oxygen. I need to cancel moles of O. And then I need to get into grams of O. That's going from moles of B to mass of B. That's using what? The molar mass. What is the molar mass of oxygen? Not water, oxygen. 16 grams in 1 mole. And based on the chemical formula, how many moles of oxygen in 1 mole of water? 1. 1 times 1 times 16 divided by 1 times 1. 16 grams of oxygen. So the next time you guys fill up a water bottle, know that you are able to calculate the mass of oxygen in that water when you weigh it out. All right, and then we've got our 3-step conversion. What is the mass in grams of copper 1 iodide that can be made with 63.5 grams of iodide? Where do I start on my roadmap? Grams of A or grams of B, doesn't really matter. By the way, I wanted to kind of point this out because I know it's not always obvious. This is where I'm starting. I have a mass of A. I need to convert into moles of that thing before I can convert into moles of something else. And then I can convert into the mass of that something else. So I give you this roadmap so that you can visually see what conversion factors you're going to need. 63.5 grams of iodide, I minus. What is the conversion factor that I need? I need the molar mass of iodide. That's going to be grams of iodide on the bottom, moles of iodide on the top. No numbers. Keep going. What next? Moles of A to moles of B. I already have moles of A. That goes on the bottom. Moles of iodide. What is the other compound I'm looking for here? What's the chemical formula of copper 1 iodide? CuI. No numbers. Keep going. I don't want to stop here with moles of copper iodide. I need the molar mass of copper iodide. I'm just setting up my units. Moles of copper iodide go on the bottom. What goes on the top? Grams of copper iodide. Hey, that's what I wanted to find out in the first place. I wanted to find out what mass of copper iodide I could make. Notice how my units cancel. Grams of iodide cancels with grams of iodide. Moles of iodide cancels with moles of iodide. Moles of copper 1 iodide cancels with moles of copper 1 iodide. Now, I can fill in the numbers. Why waste the time writing out all those numbers if you have an issue with your units? The units guide your conversions. What is the molar mass of iodide? 126.9 grams in 1 mole. Do I have 1 mole? No, I have less than 1 mole because I don't have that many grams. What is the mole-to-mole ratio between iodide and copper 1 iodide? It's 1 to 1. There's 1 iodide in copper 1 iodide. What is the molar mass of copper 1 iodide? 190.446. How do I know that that's per 1 mole? Because you calculated it. If you add it up on the periodic table, it's per 1. That's what the periodic table tells us. All right, we plug it in. 63.5. Oh, man. 63.5 times 190.46 divided by 126.9. Let's gauge. Do you think this is going to be a heavier mass or a lighter mass than what we started with? I have 63.5 grams of iodide. Will it be heavier than that with copper iodide or lighter than that with copper iodide? Heavier because I'm adding in now the mass of copper as well. Tell me if you guys get this number. 95.3 grams of copper iodide. Okay. How do you feel on conversions? What questions do you have? Okay. On the back side, 2 topics. Percent composition and empirical formulas. Percent composition is incredibly straightforward. This is literally what mass of your component divided by the mass of the entire thing. Mass of component divided by mass of compound times 100. There are 2 ways to calculate percent composition. If you are given the masses of a sample, then you can just figure out how much each of those components make up in that mass. The other is from a chemical formula. In this case, you don't have a specific amount of a sample. You just use the chemical formula. You use the molar masses of the individual pieces and the chemicals. The top question number 7. What is the percent composition of carbon, hydrogen, and oxygen in a 174 gram sample containing 100 grams of carbon, 18 grams of H, and 48 grams of O? Let's calculate percent composition of carbon together. What is the mass of the component of carbon? 108 grams. What is the mass of the compound? 174 times 100. What do you get? Yeah, let's round this. I guess we do get 3 sig figs with no, actually we have 18 and 48, so we're limited to 2 sig figs throughout this whole thing. So let's just round to 2 sig figs. 62% carbon. Once you calculate either hydrogen or oxygen, you don't even have to do the third calculation. For the third calculation, you could just do 100 minus the 2 calculations you've already done. You're just finding what's left over. Let's look at the bottom one together, because I want to work out this chemical formula with you guys. What is the percent composition of nitrogen in magnesium nitride? What is the chemical formula of magnesium nitride? Well, first of all, is this ionic or covalent? This is ionic. I have a metal and a non-metal. What is the ionic charge of magnesium? Group 2 elements, magnesium 2+. What is the ionic charge of nitride? N3-. Because nitride is a group 5 element, so to get 8 electrons, 1, 2, 3 more. What's the chemical formula? Mg3N2. Oops. We cannot do this calculation before we know the chemical formula. All right, so if I want to calculate percent nitrogen, I need to know the mass of nitrogen. But there's no masses given. So I just go off the chemical formula. 2 nitrogens, 2 times 14. 2 times 14 divided by 2 times 14 plus 3 times, oh, I don't know my masses that well, 24.3. I'm going to rewrite this a little bit larger so that we can see it. Oops. Percent nitrogen equals 28 over, what's that mass you guys are getting? You guys aren't getting it because you're just plugging it straight in, and that's okay. 100.9. What a nice little number. 28 divided by 100.9 times 100. Magnesium nitride is about 28% nitrogen. Okay, I trust that you guys are able to do this on that remaining question with oxygen. So I actually want to move on to talk about empirical formulas. We've talked about this before. Can you remind me what an empirical formula is? Lowest ratio of subscripts in a chemical formula. Some compounds, their chemical formula is their empirical formula, but for many compounds, their empirical formula is some lowest ratio of subscripts. We can calculate empirical formulas. There are, again, two ways that we can do this, but I'm going to set up a list of rules that we can follow. This is either from mass samples again, or it's from percent compositions. Here are the list of rules that I like to follow when doing an empirical formula calculation. First, convert percentages into masses and just give it the unit grams. You'll notice that step 1 doesn't apply if you aren't given percentages. It only applies if you're given percentages. If you're given masses directly, skip step 1. Step 2, convert those masses into moles. If I have 62% carbon, then I will imagine that this is 6% carbon, 62 grams of carbon. If I have 62 grams of carbon, divide by 12, I get how many moles of carbon I have. Number 3, divide all moles by whatever smallest number you get. This is going to set all of the subscripts relative to 1. Although sometimes an empirical formula doesn't have a subscript 1 in it, in which case you get these fractions. So find multiples in order to get to whole numbers. For instance, if you have something like 1 and 3.5, then you'll report this as 2 and 7. Find multiples to get to whole numbers. And then the last step is write the empirical formula. I've given you 2 examples of this. I want you guys to actually do those on your own. What I want to do is come back to this earlier one and determine the empirical formula for question number 7. So if we calculated that there is 62% carbon, did anybody calculate how much hydrogen there was? 18 divided by 174. I'm sorry. We've got 10% hydrogen. And 28% oxygen. Step 1, convert those percentages into masses. I don't know how much of a sample I have, but what if I had 100 grams? 62% of 100 grams is 62 grams. So this is step 1, convert percentages into masses. 62 grams of carbon, 10 grams of hydrogen, 28 grams of oxygen. Step 2, convert masses into molar masses. Let me give an example of what we're going to do here. 62 grams of carbon, converted into moles of carbon. What numbers do I need for this conversion? What goes on top? What goes on bottom? 1 mole of carbon weighs 12 grams. 62 divided by 12, I get 5.167 moles of carbon. 10 grams of hydrogen, 1 gram per mole. I've got 10 moles of hydrogen. What is the molar mass of O? Chemical formula or periodic table, molar mass of O? Yeah, 16. So 28 divided by 16, 1.75 moles of O. Given a percentage or given a list of masses, I can convert that into how many moles of those compounds I have. Now I divide by what? I'm going to divide everything by 1.75. So if you want to see that written out, I'm dividing each of these numbers by 1.75. Out front, I get 2.95 moles of carbon. .71 moles of H. You guys okay? You're getting the same numbers or you're getting different numbers? Okay. And 1 mole of O. All right, I think I actually propagated some error into our problem. By rounding these percentages, I think I propagated some error. And that's not great. But the other problems that you have, they shouldn't have any propagation of error. In this example, you can see that I can't easily multiply to get to a whole number. 2.95, what am I going to multiply by to get to a whole number? This is actually 3. And 5.71, what am I going to multiply by to get that to a whole number? That's actually 6. So I'm doing some rounding in my calculation here. Step 4, write the empirical formula. What is my empirical formula? CHO. C3H6O. There are a lot of compounds that have that empirical formula. One of the other conversions you need to be able to do is find a molecular formula given an empirical formula. So now I know the empirical formula is some ratio 3 carbons to 6 hydrogens to 1 oxygen. But what is the molecular formula? You'll notice that this is actually what the bottom one gives you. It says what is the chemical formula, for a compound that has a molar mass of 89 grams per mole. I want to do it with this one. What we're going to do is multiply, excuse me. We're going to take the molar mass divided by this empirical mass, and we're going to get a multiplier. So for this compound, we have a molar mass of 58. This is something that has to be given to you in a problem. It is not something that you can determine on your own. If you're not given the molar mass, you cannot determine the molecular formula. Let's say that we're given the molar mass 58 grams per mole. What is our empirical mass, given that we have C6H6O? 3 times 12 plus 6 plus 16, 58. What is 58 divided by 58? 1. My empirical formula is my molecular formula. This is the molecular formula of acetone. Okay, let's imagine that we had been given a molecular mass of 116 grams per mole. When you plug this in, you'll find that N equals 2. Your molecular mass is twice as heavy as your empirical formula. So then you get C6H12O2. You multiply the empirical formula by that multiplier to get your molecular formula. You will get problems where the empirical mass and the molecular mass are the same. You'll get problems where the empirical mass and the molecular mass are different. You just multiply. I'm afraid I can't let you guys solve these problems just yet because we've got a lot more to finish up before we head out today. So I want to turn your attention to the next packet. But you've got these practice problems to keep applying these steps to after you leave today. And of course, you've got your homework. Can you tell me what's different about the roadmap on this second page compared to the roadmap on your first page? Molarity is included. There's a new step into the roadmap. And it shows you how moles of something relates to molarity. This whole unit, this whole module, module 13, it's all about concentrations. And the first concentration to introduce, one of the most common concentrations in all of chemistry, is molarity. It's given the unit capital M. And it's a ratio. All concentration is a ratio. This is a ratio of moles per 1 liter. Kind of like miles per hour, moles per liter. There's a few things that you can do with concentration. If you know any of those 2 things, you can solve for the third. And that's why I've given you this component to your roadmap. If you know moles and molarity, you can find the volume. If you know moles and volume, you can find the molarity. If you know molarity and volume, you can find the moles. So question number 12, it says, what is the molarity of a solution containing 4 grams of sodium hydroxide in 1 liter of solution? Well, I don't have moles, do I? What I actually have is mass of sodium hydroxide. I need to convert mass of sodium hydroxide to moles of sodium hydroxide, and then I can convert to molarity. 4 grams of sodium hydroxide, what's that chemical formula? NaOH. Grams of NaOH into moles of NaOH. And once I get to moles of NaOH, I actually just want to divide by the number of liters. Here it tells me that it's per 1 liter. If this feels weird to you to have empty spots in your conversion, just get comfortable being uncomfortable. Because this is going to give me units of grams cancels, moles per liter. That's what I want. I want molarity, moles per liter. What numbers do I put in here? Well, sodium has a molar mass of 23. Hydroxide has a mass of 16 plus 1, 17, 40. 1 mole of sodium hydroxide weighs 40 grams. 4 divided by 40, not 10, not 10. 0.10. 0.1 molar. It is equally correct to put moles over liter or capital M. But that's the whole point of capital M, is to surmise moles per liter. Notice how number 13 changes. What is the concentration of nitrate ions in a sample of 1.5 molar sodium nitrate? I know the concentration of sodium nitrate. That means I can... No, let's walk through this one too. Saint, what's your question?
I was gonna ask, what can we put in that empty box above the 1 liter so that it's not?
You can put a 1. 1 will never change your mass or your numbers. It's also the same here. 40 grams per existence, 1. And 1 per 1 liter, it's just 1. I'm just dividing by liters there. Let's look at number 13. I want to know the concentration of nitrate ions in a sample of 1.5 molar sodium nitrate. .5 moles of sodium nitrate per liter. I want to convert from moles of sodium nitrate into moles of nitrate. A mole-to-mole conversion, and I'm not getting rid of liters here. 1 mole of sodium nitrate has 1 mole of nitrate. Pick a different chemical, your mole-to-mole ratio changes, and you can change the concentration that way. You'll see a similar problem when you look at 14. How many moles of sulfite ions in a 2.1 molar solution of iron 3 sulfite? Notice here how I actually never needed to change liters. I just took care of moles and I left liters where it was. On the backhand side, I'm sorry guys, I would love to spend more time on these, but I also want you to see them. On the backhand side, we talk about dilution. Dilution is actually one of the equations on your midterm equations chart. It's written as C1V1 equals C2V2, but it can be written different ways. Sometimes it's written M1V1 equals M2V2, where M is meant to be molarity. But if you're not working with that specific unit, then you can say C1V1 equals C2V2, where C stands for concentration. Dilution is where you take a specific number of moles and you just distribute it into a more dilute system, a more dilute solution. For instance, M1 times V1, moles over liters times liters is moles. M2 times V2, moles per liter times liters is moles. The dilution equation is saying I have this many moles and I still have this many moles. But I had this many moles in this concentrated of a solution, and now I've diluted it to get a less concentrated solution. Dilution is a way of taking moles and diluting them. So let's solve one of these problems together. A sample of 1 molar hydrochloric acid needs to be diluted to 200 milliliters at 0.1 molar. What initial volume of 1 molar HCl needs to be used? M1V1 equals M2V2. I know M1. It's 1 molar. I know M2. It's 0.1 molar. I know V2. It's 200 milliliters. What do I not know? And that's what I want to find out. The initial volume. So can I do some algebra and just set this equation up before I plug in any numbers? I'm going to divide by M1 so that V1 is alone. V1 equals M2V2 over M1. What was M2? 0.1 molar. What was V2? 200 milliliters. What was M1? 1 molar. Talk to me about units. What's going on with the units here? Molars cancel. Molar divided by molar. I'm left with units of milliliters. The question doesn't actually say what volume it should have or what units the volume should have. It is true that molar is moles over liters, but if molar and molar cancels, this can be liters, milliliters, microliters, doesn't matter, because the volume is actually not changing here. What do I get? 20 milliliters of solution. If I take 20 milliliters of a concentrated solution and I dilute it to 200 milliliters, I get a less concentrated solution. I'm taking the same number of moles, and I'm just spreading them out over a larger solution. All right. I trust you guys can do more with dilutions. It takes some practice, but I want to point out a tip that I used in this write out all your variables and what they're equal to. Because that actually helps you identify an equation to use. Oh, I've got an initial concentration, a final concentration, a final volume, and I want to know an initial volume. Now I know I need the dilution equation. Write out all your variables, and then plug them in as you need to. There are a few other concentrations that we talk about. One of them is the mass percent. And this is the mass of a sample over the mass of a solution times 100. In the same way, we have the volume percent. I'm sorry, I want to change a small thing about that. I said mass of sample. I think it'd be better here to say mass of a compound. For instance, if I'm looking at the mass of sodium chloride dissolved in the mass of 100 grams of seawater, I'm looking at the mass of the sodium chloride, that component, that compound. The volume percent is pretty much the same. We're looking at the volume of a solute divided by the volume of a solvent times 100. Can someone tell me, inside of a solution, what is a solute versus a solvent? Solute is being dissolved. Solvent is doing the dissolving. And then we get this, which is ppm and ppb. Those stands for parts per million, parts per billion. How come we don't do parts per hundred? Trick question. You do. That is what you're doing when you multiply by 100 up there. You're doing parts per 100 parts. That's all it is. Parts per million, parts per billion. This is the mass of your component divided by the mass of the solution times a million. Just like how you do times 100, that's basically parts per 100. Percent. Actually, you are saying it. Per cent. A century is how many years? 100 years. Percent is per 100. Parts per billion, mass of a component divided by the mass of the solution times what? A billion. 10 to the 9. Here's what I'm going to do with this worksheet, guys. I'm going to record a video today of me solving this, and I'm going to upload it to Canvas so that you guys can practice this on your own and then watch the video afterwards to see what you did right, what mistakes you might have made, and how to improve your skills with doing these conversions. All right? Okay. Happy fall break to you. Your unit test is due what day? Monday. Please don't take it Monday. Try to take it as early as you can. Who has scheduled their midterm exam? That's a much better distribution of hands. Great job. Your midterm goes until the Monday after next week, but you all know when you're taking it. Review next week. No attendance necessary. But if there are no questions to review, then I will be moving on into our new material. All right, have a great weekend. I'll see you next week. Maybe. Thank you.